Hi, today I'm going to solve the question in chapter 16.8, the divergence theorem and a unified theory. Use the divergence theorem to find outward flux F across the boundary of the region D. F equal to x squared I plus y squared j plus z squared k. Part A, cube D, the cube cut from the first octant by the planes x equal to 1, y equal to 1, and z equal to 1. Part B, cube D, the cube bounded by the planes x equal to positive negative 1, y equal to positive negative 1, and z equal to positive negative 1. Part C, cylindrical can D, the region cut from the solid cylinder x squared plus y squared less than or equal to 4 by the planes z equal to 0 and z equal to 1. First of all, what you need to do is differentiate each variable. D over dx, x squared equal to 2x. D over dy, y squared 2y. D over dz, z squared 2z. Then with this differentiate, we can rewrite it as beta f equal to 2x plus 2y plus 2z. After that, we need to find the flux. So we use triple integration of the function dx, dy, dz. The limit for x equal to 1 to 0. The limit for y is also 1 to 0, and limit for z also 1 to 0. So now we integrate this function. 2x squared over 2 plus 2xy plus 2xz between 1 to 0 is equal to cancel, so 1 plus 2y plus 2z, because we don't have to substitute 0 because all the parts become a 0. So now we get this equation and we have to integrate the y variables. So it gives y plus 2y squared over y and 2 plus 2yz between 1 to 0. So it gives 1 plus 2z. So it becomes 2 plus 2z. Then we need to differentiate the z variable between 1 to 0. It gives 2z plus 2z squared over 2. So cancel, so 2z plus z squared between 1 to 0. It gives 2 plus 1. So the flux for part A is 2 plus 1 equal to 3. Now we do the part B. So earlier the question said the cube bounded by the planes x equal to positive negative 1, y equal to positive negative 1, and z equal to positive negative 1. So we use the same flux, 2x plus 2y plus 2z. We integrate this function 2x plus 2y plus 2z between 1 to negative 1, 1 to negative 1, 1 to negative 1, because the question said the cube bounded by the planes x equal to positive negative 1, y equal to positive negative 1, and z equal to positive negative 1. Y dx, dy, dz. So now we integrate the function. So 2x squared over 2 plus 2xy plus 2xz between 1 to negative 1, it gives cancel, so 1 plus 2y plus 2z negative 1 plus minus 2y minus 2z. So 1 plus 2y plus 2z minus 1, positive 2y, positive 2z. So 1 cancel, so become 4y plus 4z. So now we integrate the y variables. So equal to 4y squared over 2 plus 4yz between 1 to -1. It gives a 2y squared plus 4yz between 1 to -1. So it gives 2 plus 4z negative 2 negative 4z. So it's simplified as -2 positive 4z, -2 cancel, it becomes 8z. Now it's time to integrate the z variable. So integration 8z between 1 to -1 is equal to 8z squared over 2 equal to 4z squared. So between 1 to -1, so 4 minus 4, it becomes 0. So the answer for part B is equal to 0. The time to solve the part C is the last question. The region cut from the solid cylinder x squared plus y squared less than or equal to 4 by the plane z equal to 0 and z equal to 1. This question also we use the same equations 2x plus 2y plus 2z, but we need to convert it this equation because since the question says a cylindrical can x equal to r cos theta, y equal to r sin theta. We use this formula, we sub it in 2r cos theta plus 2r sin theta plus 2z. Now we have to integrate it. We got the new equation, so we triple integrate to find the flux. So it's a r d theta dz. The limit between the r is equal to 0 to 2, and then the d theta equal to 0 to 2 pi, and then the z part is 0 to 1. It's because the previous say the equation of the solid cylinder is x squared plus y squared less than or equal to 4. So which means the radius of this function is equal to 2. Therefore the limit is equal to 0. And then the theta is the whole circle, we need to find it, so equal to, the limit for this one is 2 pi, 0 to 2 pi. And then the z is 0 to 1 because the question says so. So we integrate 2r cos theta plus 2r sin theta plus 2z r d theta z. We need simplify first. 2r squared cos theta plus 2r squared sin theta 2rz dr d theta dz. We write in as 0 to 0 2r squared cos theta 2r squared sin theta plus 2rz dr d theta dz. So we get at this equation, so we integrate 2r cubed over 3 r cubed over 3 cos theta plus 2r cubed over 3 sin theta plus 2r squared over 2z between 2 and 0. So it's equal to 2 over 3 r cubed cos theta plus 2 over 3 r cubed sin theta plus r squared z between 2 and 0. We don't have to submit in 0 because later we all become 0, so we just submit in the 2. So it's equal to 16 over 3 cos theta plus 16 over 3 sine theta plus 4z. We got the new function, so we integrate again. Theta plus 16 3 sine theta plus 4z between 2 pi to 0 d theta is equal to differential integration of cos theta equal to sine theta. Sine 16 over 3 sine theta. Integration of sine theta is negative 16 over 3 cos theta plus 4z theta between 2 pi to 0. We sub in the value 2 pi, so sine 2 pi is equal to 0, so we don't have to do. Cos 2 pi is a negative 1, so 16 over 3 plus 8 pi z negative cos theta equal to 1, so 16 over 3 plus 0. Simplify, 16 over 3 plus 8 pi z negative 16 over 3 plus 0 equal to 16 over 3 cancel 8 pi z. So now we need to integrate this part. 8 pi z between 1 to 0 dz equal to 8 pi z square over 2 between 1 to 0. 2 cancel 4 pi z square between 1 to 0 is equal to 4 pi. So the answer for part C is a 4 pi. So thank you for watching my video. See you next time. Bye.